Welcome students. In the last session, we had a discussion over Kirchhoff's laws. Then even we had a discussion over Wheatstone's network, a practical form of a Wheatstone's network, that is a meter bridge. So all these things we have discussed. So today we are going to wind up this chapter electric current with a discussion over one more instrument called potentiometer. When I say it is an instrument, obviously it is used for some purpose. Before I tell you the description of the potentiometer, let me tell you what is a use of this instrument. This instrument can be used to compare the EMF of the two cells. This is a one application. Even using this instrument, you can determine or you can find out the internal resistance of the cell. So as it has been already informed to you in the beginning of this particular topic. In your physics practicals this year, there are around 5 experiments which you are going to perform from this particular chapter, Out of the 5, 2 I have mentioned in the last session related to a meter bridge, right? And another 2 experiments which you are going to perform in the physics lab this year is these 2 experiments. So listen carefully, helpful a lot for your practical session also. These are 2 separate experiments using a potentiometer. Using potentiometer, it can be used to compare the EMF of the 2 cells. It can be used to determine the internal resistance of the cell. We are going to discuss in detail. So before I take up one by one, let me describe what is potentiometer. Let me also explain you the basic principle behind the working of a potentiometer. Then we will move on to the experiments. Okay. So we will begin with the description of the instrument potentiometer. Nothing special. This instrument consists of a rectangular wooden board, just like your meter bridge consists of a rectangular wooden board. On this wooden board, there are 2 terminals fixed. For your reference, I don't mind naming one terminal as terminal A and other terminal as terminal B, terminal A and terminal B. Between these 2 terminals, A and B, there is a wire, uniform wire. When I say uniform, throughout the length of the wire, thickness is same, and of length 1 meter. Even we can have an instrument, there is a wire used of length 4 meter also, but in my explanation I will stick on to a potentiometer having a wire of length only 1 meter. This wire is not a copper wire, it is not a single metal, it is an alloy. Just like your meter bridge, here also we prefer nichrome or constantine or manganine, because these material have got high resistivity. What is the use of high resistivity? What is the advantage of high resistivity? Smaller length of the wire itself is sufficient to have a high resistance, and they have a low value of alpha, temperature coefficient of resistance, means their resistance do not vary much with the temperature. So there is an alloy wire of length 1 meter fixed between A and B, and of course there is a meter scale below the wire, just like your meter bridge, there is a meter scale. This is potentiometer. Nothing much, simple arrangement, wooden frame, there is a wire made up of an alloy is fixed between the 2 terminals, and there is a meter scale. Of course, in between I said, we can have a potentiometer instrument where the length of the wire can be 4 meter, means 400 centimeter. Now the thought may come in your mind, if it is 400 centimeter means whether the length of the wooden frame is 4 meter? No. So it will be of same length. I'll just draw the schematic diagram of that also, just for your reference, because in your lab you may be using a potentiometer where the length of the wire may be around 400 centimeter. What they do is, they'll use a same length wooden frame and they will take a 4 nichrome wire or constantine or a manganese wire, each of length 1 meter, and it is fixed on the wooden frame like this. This is one nichrome wire of length 1 meter. This is a one more nichrome wire of length 1 meter. This is a one more nichrome wire of length 1 meter. This is one more. Each is of 1 meter, means totally 4 meter, no? But it should act like a single wire of length 4 meter. So what they do is, if you start from here, if this is termed as a terminal A, here these two ends of the wires are joined by a metal strip. That metal strip is having a negligible resistance. These two are joined by a metal strip. See, from here to here 100 centimeter plus 100, totally 200. Then again till here 300. Again there is one metal strip here. This end is taken as a terminal B. Don't you think? Now I am having a potentiometer instrument where the length of the wire is 400 centimeter or 4 meter. I hope you followed this. This is just for your reference. Later you should not get confused if you come across a potentiometer of length 4 meter. A and B will be here. Okay? Fine. So let me proceed. So I already described the instrument, how the instrument looks. Let me take up a discussion over a principle behind the working of the instrument. To understand the principle, I have to include certain things in my explanation. So from A and A, I have to take a connection. You connecting wires are always copper wires because they have a negligible, very small resistance. Other end of the copper wire, I need to connect it to a battery. I need to connect it to a battery. Battery can be a combination of cells. And the negative of the battery is connected to end B. Negative of the battery is connected to end B. Just to get a better idea, I will give some number here. Assume that EMF of the battery used by me is 5 volt. EMF of the battery is 5 volt. Then take a connection from A, again copper wires. Other end of the wire is connected to an instrument called voltmeter. You are familiar, even this voltmeter is also one of the ohmic device. Ammeter, voltmeter, in the last session I mentioned about galvanometer. They are all ohmic devices. Voltmeter is an instrument used to measure a potential difference. Other end of the voltmeter is connected to, any idea? In the last session we have come across this type of a diagram. Yeah, it was a sliding contact or a pointer or a joystick key, which we also in a short form we call it as a jockey. Sliding contact or a pointer or a joystick key. I told you about this sliding contact. It is a metal contact actually, almost of this size, of the size of the chalk piece here, and it is a metal contact. One end there is a terminal where I can slightly open the terminal and I can fix this copper wire and tighten it. Other end is a sharp end, and entire metal contact is covered by an insulator so that you can handle it properly without getting any shock. Okay. Now you just compare my discussion, what I am going to have here, with a simple circuit consisting of a cell and an external resistance, what you have learnt earlier. I will just recall for your reference. Let us say there is a cell cell is having an EMF E, internal resistance small r, and this positive terminal of the cell is connected to a resistor, and the other end of the resistor is connected to a negative terminal of the cell. You know that based on your knowledge, I can expect a current, conventional current will be I. Since it is a single branch, as long as it is a single branch, current throughout it will be same. And based on your earlier knowledge, this V will be equal to V plus V dash. E will be equal to V plus V dash. E is a EMF of a cell. V is a potential drop across the external resistor. V dash is a potential drop across the internal resistance of a cell. E is called EMF of a cell. V is called potential drop across the external resistor. In the above formula, V is called a potential drop across the external resistor. Even it is also called as a potential difference across the terminals of the cell. It is also called as a potential difference across the terminals of the cell. I hope you followed this. Potential difference across the terminals of the cell. See here, this V, which is called as a potential difference across the terminals of the cell, it is also called as a terminal potential difference. You already know it. It is also called as a terminal potential difference. This V dash, it is a potential drop across the internal resistance of a cell. I'll repeat, this V is called potential difference across the terminals of a cell, which is also called as a terminal potential difference. Here I don't mind to say that it is a potential difference across the external resistor. If I connect a voltmeter, across this resistor, or if I connect a voltmeter across the terminals of the cell, if I say that I am using the cell of EMF around 1.5 volt here, ordinary everyday or adipose cell, dry cell, its EMF, if I say it is 1.5 volt, what do you think this voltmeter reads? Do you think it reads 1.5 volt? No, it will always read less than 1.5 volt. If I say this voltmeter is reading around 1.3 volt, even this voltmeter also reads nearly 1.3 volt only. For your kind information, this point and this point will be at same potential. This point and this point will be at same potential. When I say positive, this point and this point are at same potential, and this point and this point are at same potential, don't you think that both the voltmeter should read the same reading? Yeah, see, keep in mind, this is a connecting wire, copper wire, they have a negligible resistance. Since they have a negligible resistance, there is no much potential drop. There may be a very small potential drop. What I mean to say is, if this is 1.3, this may be 1.29. 1.29. That difference is ignored. So based on this logic, I said V is a potential difference across external resistor that is equal to potential difference across the terminals of a cell that is equal to terminal potential difference. You need to remember this. Based on this logic only, I said that V in the above equation can be called as the potential difference across the external resistor, or potential difference across the terminals of the cell, or terminal potential difference. Don't you notice that terminal potential difference is less than the EMF of the cell? 1.3 is less than 1.5. No, EMF of the cell I have taken it as 1.5. Terminal potential difference is less than the EMF of the cell. It is always true when cell is in the closed circuit. CKT represents circuit. When cell is in the closed circuit, terminal potential difference is always less than the EMF of a cell. See, I don't repeat all this discussion. You have to remember these points. Terminal potential difference or potential difference across the cell is always less than the EMF when the cell is in the closed circuit. Now the question is, when we say that the cell is in the closed circuit, Cell is said to be in the closed circuit when current was drawn from the cell. By the circuit or by the circuit element. The cell is said to be in the closed circuit when the current was drawn from the cell by the circuit element. One more point you need to remember. There is something called cell being in the open circuit. You have studied this in a cell. You have to go back and you refer. You know, one of the equation you come across was terminal potential difference. Terminal potential difference V is equal to ER by R plus small r. Correct? If you divide both the numerator and denominator by R, you will be going to get V is equal to E by small r by capital R. Correct? There, you have come across situation, mathematically thinking for a time being, if capital R is equal to infinity, don't you think that V is equal to E? Capital R is equal to infinity means R is infinite. Something by infinity will be 0. 0 plus 1 will be 1. E by 1 will be E. See? Here I said V is less than E. Here what we are proving is V is equal to E. Of course, you may be knowing one more factor. If small r is equal to 0, 0 by something will be 0, 0 plus 1 will be 1, E by 1 will be E. That time also V is equal to E. Means V will be equal to E when small r is 0. But that is okay as far as problems are concerned. When you are having a cell of negligible internal resistance, V will be equal to E. But in reality, in practice, each and every cell has got some internal resistance. There is no cell without any internal resistance. The internal resistance may be a very low value, but it is not 0 in reality. Only in the numericals, if they say that there is a cell of negligible internal resistance, you can ignore small r and you can take V is equal to E. That is in the problem. But practically speaking, small r will never be 0. And what about this? Capital R being equal to infinity. Capital R being infinity means opposition is infinity, means we expect that there should not be any current. That is possible only when the cell is in the open circuit. Just to open the circuit here, if I just open the circuit there, see, I am talking about the same cell of EMF, how much, 1.5 volt, I am not going to change the value, and here you are having a voltmeter. Remember, this voltmeter will read 0. Because for the working of the voltmeter also, it will draw very small microampere current. This I may be ampere, but for the working of the voltmeter, it requires a small amount of microampere current. Why it draws very small current? Because its resistance is very high. But here there is no current at all, because when you open the circuit, but sorry, not this V, this V will be 0. Sorry, this V will be 0. There is no current, but this V will be 1.5. Not this V. Listen. The voltmeter connected across the resistor will read 0 because there is no current here, whereas this voltmeter connected across the terminals of the cell, it is not 0, I made a mistake in that. This will read suddenly 1.5. It was reading 1.3 earlier, now it is reading 1.5. That is the meaning. Now you can say that cell is in open circuit. Of course, you may be thinking, here the circuit is closed. No, it is closed. But how much current voltmeter will draw? Very small amount of current that is needed for its working. That is why this voltmeter is reading 0, because it is not able to work. There is no current drawn because this circuit is open. Whereas this may draw very small amount of current that is negligible compared to your ampere current. So this voltmeter will read 1.5, which is same as EMF of a cell. Which means now I can say that terminal potential difference is equal to EMF of a cell when the cell is in the open circuit. Next question is, what do you mean by cell is in the open circuit? Cell is said to be in the open circuit when no current was drawn from the cell. Drawn from the cell by the circuit elements. So the intention of recalling this discussion is just to highlight these points. You please remember this, very much needed for my explanation. See, voltmeter connected across the cell which was reading 1.3 volt there, now it will read nearly 1.5 volt when you open the circuit. Here we say that the cell is in the open circuit, here we say that the cell is in the closed circuit. So ultimately what you need to remember is this. Terminal potential difference, please keep in mind, terminal potential difference is always less than the EMF of a cell when the cell is in the closed circuit, and cell is said to be in the closed circuit when the current was drawn from the cell by the circuit element. Terminal potential difference will be equal to EMF of the cell when the cell is in the open circuit. Cell is said to be in the open circuit when no current was drawn from the cell by the circuit elements. I think you understood this. So this is needed, especially these 2 points you need to remember, that I am going to use in my discussion. Okay? Fine. Okay, now come back to this. I was talking about the principle, basic principle behind the working of a potentiometer. Battery is switched on. Take the sliding contact. Keep the sliding contact in contact with the wire, let us say at some position here. So don't think that many sliding contact there, it is only one sliding contact. I am keeping it in various position. When the sliding contact was kept in contact with the wire at C, can I expect some reading in the voltmeter? Yes. Don't you think voltmeter is connected across A and C? Surely it will read a potential difference. Correct? Fine. If I shift a sliding contact to the next spot on the wire, let us say D, don't you think now also voltmeter will read some reading? What do you think? The reading read by the voltmeter is more than earlier or less than earlier or same as earlier? It has to be more than earlier. Why you think? If I shift a sliding contact to a next spot on that alloy wire, don't you think voltmeter reading will keep on increasing? If you shift to the next spot, voltmeter reading will increase. You know why? We know that V is equal to I into R, mathematical form of Ohm's law. V is a potential difference across the 2 points on this wire read by this voltmeter. According to your knowledge, you know that resistance is directly proportional to length. If I substitute the formula for resistance, rho L by A, don't you think resistance is directly proportional to length? As length increases, resistance also increases. When resistance increases, since current is same throughout, potential drop also goes on increases, because V is directly proportional to R when I is constant. When I is constant, when R increases, potential drop also increases. No, that is a logic. That is why you find that voltmeter reading keeps on increases, and moreover in this experiment which I am performing now in convincing you the principle of a potentiometer, don't you think that I rho by A is a constant? I am not going to change the current in the circuit in between. I am not going to change the material of that wire fixed between A and B. So rho is fixed, A is fixed, means can I write V is directly proportional to L. This is a constant, I can represent as phi, I don't mind. I rho by A is a constant. So which means V is directly proportional to L, indicating that V by L is a constant. A to C, A to D, A to E, A to F, A to B, length goes on, increases. When the length goes on increases, even potential difference goes on, increases. When you write V is directly proportional to L, obviously V by L will be a constant. Think, what is V by L? V by L is called potential gradient. V by L is nothing but a potential gradient. Potential gradient is a constant. That is a basic principle behind the working of the instrument called potentiometer. V is directly proportional to L. Potential difference between the 2 points on the wire is directly proportional to the length of that portion, or V by L is a constant. V by L is called potential gradient. Potential gradient is a constant, or V is directly proportional to L. This is a basic principle behind the working of potentiometer. I hope you understood this. Okay. So with this basic principle, let us start our discussion with reference to the first experiment to compare the EMF of the two cells using a potentiometer. And one more thing I forgot to tell you. When I keep a sliding contact in contact with the wire at B, what the voltmeter will read? Does it read 5 volt? No. It will read less than 5 volt. See the reference. What is the potential difference across a resistor? 1.3. That is not equal to EMF. EMF is more than that. Same logic here. When you keep a sliding contact in contact the wire at B, it will read a reading which will be less than 5, because some potential will be dropped across the internal resistance of a cell also. Correct? Okay. We'll start with the first experiment. Compare the EMF of the two cells. No change in the potentiometer. It is the same wooden frame. There are two terminals. Between the two terminals, there is a alloy wire of length 1 meter. Fixed. Again, no change in the upper part of the circuit connections in the diagram. From A, using copper wire, connection is given to the positive terminal of the battery. I'll use the word battery for this. The negative terminal is connected to you can use a rheostat. You will be using a rheostat in your practicals. What was the rheostat? In the previous session, in one of the session earlier, the sir has explained to you. It is used to vary the current in the circuit or to vary the voltage in the circuit. They use a rheostat. A rheostat will be used only when you are performing a number of trials. See, in the previous explanation, I told you V is equal to IR, V is equal to I into rho L by A, where I rho by A is a constant. It is a constant for one trial. Purpose of using a rheostat is for the next trial you will be varying the constant. Next trial, constant will be different because you will be changing the current. For one trial, current is fixed. For next trial, you are going to vary the current. So I need a rheostat. Battery and a rheostat. By varying the knob in the rheostat, you can vary the current. When the current varies, this constant will vary. That is the purpose of using a rheostat in your experiment, because you will be performing a number of trials. I need not use a rheostat because I am explaining only one trial. Understood? And there is something called variable battery also. So this is a circuit symbol of a fixed battery. Fixed battery, where in the battery there is no option to vary the voltage. If you want to vary the voltage and you are using this battery, you have to include a rheostat in the circuit. By using a rheostat, you can vary the voltage. But nowadays we have a battery where rheostat will be inbuilt in it. Rheostat will be inbuilt, and such a battery we represent by the symbol, a cross arrow mark. In that battery there is one option one extra knob will be there. By turning the knob, you can vary the voltage or a current. You don't require a rheostat for that. This is a circuit symbol of a fixed battery, this is a circuit symbol of a variable battery. If I am having a variable battery, I don't require an additional rheostat. By turning the one extra knob given in the battery, you are varying the voltage. That means in such battery, rheostat is inbuilt. Understood? So this is actually original circuit where I have to include a rheostat. A rheostat, I told you, the purpose of using rheostat is when you are performing a number of trials. If I am not performing a number of trials, I need not use a rheostat. I will remove the rheostat later. This is called, whatever I have drawn, no, it is called primary circuit. It is called primary circuit. Now coming to the experiment. You will be given two cells. You will be given two cells. One is of EMF E1, other one is of EMF E2. We don't know both of them. I mean to say, we don't know the value of E1 and E2, but you are asked to find out what is E1 by E2. That is the meaning. To compare the EMF of the two cells. So I am using the word cells. Don't get confused with this. This is also actually a combination of a cell, but here I will use the word battery just to avoid a confusion. You will be given two cells. Let us say EMF of the one cell is E1, EMF of other cell is E2. We don't know both the values, but you are asked to find out E1 by E2. That is the meaning of the question, comparing the EMF of the two cells. Now what you need to do is, take a connection from a NDA, of course copper wire. Other end of the wire is connected to the positive terminal of one of the cell, let us say whose EMF is E1. Negative terminal of the cell, I will connect it to one key. You may be knowing about this plug key. Plug key in the sense, practically the arrangement will be, there is a rectangular frame, and there are two metal points, metal contacts, leaving the gap between them. Rectangular frame, there are two metal knobs leaving the gap between the two, and to fill the gap you will be given one metallic key having an insulation cover at the top to fill the gap. See, these are the two metal knobs where wires can be connected to those knobs, and there is a gap between these two metal knobs. This gap can be filled by the metallic key having at the top the insulation cover. Suppose if this gap is not filled with this key, we say that key is open. Key is open, and we represent open key in the circuit symbol like this. Bracket we put and two electrical leads we take, and gap is not filled, key is open. Suppose if this gap is filled with this metallic knob, don't you think that when the gap is filled with a metallic knob, these two points are in contact? Now we say that key is closed. In the circuit symbol, key is closed means we put one dot inside. We have put the key. If you remove the key means I have unplugged the key. Means circuit is open, key is open. If I put that knob means key is closed. I think you understand. There is a key K1, it is open and not close the key. When the key is open means it is just like open circuit. No current is flowing in that part. And the other end of the key, I mean to say the two ends means from one end here, one more end here, you can take a connections using the copper wire. Other end of the key is connected to a galvanometer, and now it is a galvanometer. In the principle it was a voltmeter. Now it is a galvanometer. You have seen already a galvanometer. I have already described you. And this is what? Sliding contact or a pointer. In the galvanometer, again for your reference, galvanometer, there are two terminals for the electrical connection, and zero reading is at the center. There are 30 divisions on either side of the zero, and there is a pointer reading 0 at the center. when there is no current flowing through the galvanometer. For what purpose galvanometer is used? To detect the presence of a current in the circuit. Whenever you include a galvanometer in the circuit, if the pointer in the galvanometer shows some deflection, indicates that there is current. And direction of a deflection indicates the direction of the conventional current. Even though you include a galvanometer in the circuit, if the pointer in the galvanometer shows zero deflection, indicates that there is no current flowing through the galvanometer. Keep in mind all those points. Okay, one more. Take a one more wire from A, copper wire from A, connected to the positive terminal of the another cell whose EMF is E2, which we don't know, and the negative of the cell is connected to a one more key K2, and other end of the K2 is connected to the same point, one terminal of the galvanometer where the one end of K1 is connected. The point of internet is one end of K1 and one end of K2 are connected to the same terminal of the galvanometer, and other things are as usual. The point to be noted is K1 and K2 are open, they are not closed. Okay, your involvement is needed in my discussion. I said my discussion is restricted to only to one trial. I will remove the rheostat. Rheostat is needed when you are performing a number of trials. I hope you followed the connections. Now, before you start the experiment, you have to check one thing. That is, EMF of this battery used in the primary circuit should be greater than the EMF of these two cells which is used in the secondary circuit. I can call this part of the circuit as a secondary circuit. This is a primary circuit, this is a secondary circuit. I said before you start the experiment, you have to confirm that EMF of this battery should be greater than the EMF of the two cells, E1 and E2. Next question arises in your mind is, we don't know the value of E1 and E2, then of course you may be knowing the value of a EMF of the battery, but we don't know the value of E1 and E2, then how to check whether the EMF of the battery is greater than E1 and E2? So it is a very much common sense. If you are knowing the value of E1 and if you are knowing the value of E2, why the hell you have to perform the experiment? You just substitute the values, If you are knowing E1, if you are knowing E2, substitute E1, substitute you got E1 by E2. Yeah. Now coming to your doubt, when I don't know the value of E1 and E2, how to check that whether the EMF of the battery is greater than the EMF of the two cells? What you need to do is, we'll use one by one cell in the experiment. First we will close the key K1, K2 is open. When you close key K1 and K2 is open, it is as good as saying that this part is not included in the circuit at all, yes or no? Because when the K2 is open, this is open circuit, better to remove that, no? We'll do it later, okay fine. K1 is closed. Then take that pointer, that sliding contact, whatever you call it. Keep the pointer in contact with the wire fixed between A and B near end A. We expect the pointer in the galvanometer should show a deflection to one side of the zero of the galvanometer, one side, either left side or right side, one side. Then remove the sliding contact which was in contact with the wire. Deflection will become zero. Now you keep a sliding contact in contact with the wire near end B. Now what you should expect is the pointer in the galvanometer should deflect to the opposite side, other side of the zero. Means when you keep a sliding contact in contact the wire near end A, pointer in the galvanometer should deflect to one side of the zero. When you keep in contact the wire near end B, the pointer in the galvanometer should deflect to the other side of the zero. If you observe this, then it is confirmed that EMF of the battery is greater than E1. Okay, next I have to check for E2 also. Open the key K1, close who? K2. Again repeat the same thing. When I close, when you open the key K1, understood? No, this part is of no use. You can remove that. Only I am involving the cell of EMF E2 in the circuit. Again repeat the same thing. Keep the key in contact with the wire near end A. Pointer in the galvanometer should show deflection to one side. keep the sliding contact in contact with the wire near end B, the pointer in the galvanometer show deflection to the opposite side. If you observe that, it is confirmed that EMF of the battery is greater than the EMF of each cell, second cell also. This is the first thing you are supposed to do. Next question is, what if you find a deflection at the same side when you are using either both the cell or one of the cell in the circuit? If you find a deflection at the same side, then you have to change the battery. You don't have a right to change this, because this E1 and these two cells are given to you and you are asked to compare the EMF of that cell only. If you find a deflection at the same side of the zero, when you keep a sliding contact near end A or near end B, it indicates that EMF of the battery is less than EMF of a cell. That time you have to change the battery. You have to go for a battery of higher EMF, connect here, then again check it, until you find that when you connect one by one the cell, the deflection in the galvanometer should be on either side of the zero. This is how you practically find out. I think you understood. Okay. Let us say that we have practically verified and we found that EMF of the battery is greater than E1 and E2. How you understood? When you keep a sliding contact in contact the wire near end A or near end B, deflections on either side of the zero galvanometer, indicating that EMF of the battery is greater than the EMF of the two cells. Okay, now I will close the key K1. Key K1 is closed. K2 is open. When K1 is closed, K2 is open. Don't you think that since K2 is open, it is as good as saying that it is better to remove this portion. I am removing this portion because it is of no use now, and the intention of removing that in the circuit diagram is just to make the things clear when I give some explanation in this circuit. Of course, you are not going to remove it in the experiment. That circuit will be there because anyhow K2 is open, there is no role of that part. For my convenience of convincing the point, I removed it from the diagram. Okay, K1 is closed, K2 is open. Okay, now what you are supposed to do? Take this sliding contact, keep it in contact with the wire near end A, pointer in the galvanometer show deflection to one side, then keep on moving the sliding contact in contact with the wire. I told you, better not to slide. If you slide, uniformity of the wire will be lost. I hope you are able to follow. If you slide, uniformity of the wire will be lost, so don't slide it. So here, keep on shifting the sliding contact at various positions, shifting the sliding contact slowly. You know, it was deflecting one side, so slowly the deflection goes on, decreases, correct? Assume that when the sliding contact in contact with the wire at some point C, deflection read by the galvanometer is 0. When the sliding contact was in contact with the wire, when the sliding contact is in contact with the wire at point C, deflection read by the galvanometer is 0. Of course, if you remove the sliding contact, deflection is 0. But still, even though the sliding contact is in contact with the wire, deflection is 0 means, don't you think that the current flowing through the galvanometer is 0? Yes. Now, this point you are supposed to understand. Current through the galvanometer is 0. Listen carefully. Current through the galvanometer is 0. Current through the galvanometer is 0 means, what is the current here? 0 only, because it is a single branch. Current through the galvanometer is 0 means current in this portion is also 0. Current in this portion is also 0. Current in this portion is also 0, right? Current in the entire branch will be 0. I am talking about this branch, A to the cell, cell to the key, key to the galvanometer, galvanometer to C. In that branch, current is 0 because a single branch. Deflection in the galvanometer 0 means current is 0. What is the meaning of that? Look at this. C and negative terminal of the battery. C and negative terminal of the battery. Is there any conducting path? Yes, there is a conducting path. Is there any current between negative terminal of the battery, negative terminal of the cell and negative terminal of the cell and C? No. Conducting path is there, but still there is no current, indicating that C and the negative terminal of the battery, C and the negative terminal of the cell both are at same potential. You know the basic requirement for the current, there should be a conducting path and there should be a potential difference. Conducting path is there between C and negative terminal, but still current is not there, indicating that C and the negative terminal of the battery are at same potential. Similarly, at the other side, is there any conducting path between A and positive terminal? Yes. Do you have a current? No. Indicating that A and positive terminal of the battery are at same potential. I said C and negative terminal of the battery are at same potential. A and positive terminal of the battery are at same potential, which indicates that potential difference across AC is equal to potential difference across the terminals of the cell. Potential difference across the terminals of the cell. Potential difference across AC is equal to potential difference across the terminals of the cell. Now, what do you think? This potential difference across the terminals of the cell, which you also call it as a terminal potential difference, is it equal to EMF of the cell? Potential difference across AC is equal to potential difference across the terminals of the cell. Can I say it is equal to EMF of the cell? Yes, I can say it is equal to EMF of the cell. Not always. Terminal potential difference is not always equal to EMF. In the general situation, terminal potential difference is always less than the EMF. But here I can say that potential difference across the terminals of the cell, which you also call it as a terminal potential difference, will be equal to EMF. Tell me, when we say that terminal potential difference will be equal to EMF, when the cell is in the open circuit. What do you mean by cell is in the open circuit? When no current was drawn from the cell. Look at this. This is a cell. Now I can say that cell is in the open circuit. Next doubt arises, key is closed. No, where the cell is in the open circuit. Don't always think in that in that dimension. I already explained you in detail. Cell is said to be in the open circuit when no current was drawn from the cell. Cell is here. Do you have any current in this part? No. Do you have any current in this part? No. Indicating that no current was drawn from this cell? No. No current was drawn from the cell means cell is in the open circuit. When the cell is in the open circuit, that is always equal to EMF of a cell. That means, why potential difference between the terminals of cell is equal to EMF? Because cell is in the open circuit. Don't get confused with this word open circuit. Why we say cell is in the open circuit? Because no current was drawn from the cell. Since no current was drawn, that was the reason. That was the reason to say that cell is in the open circuit. Okay, that means can I write this is equal to E now? What was the basic principle behind the working of potentiometer? V is directly proportional to L, or V by L was constant, correct? What is L? Length of this. Shall I take up this length as L1? You know, when you keep a sliding contact at C, you got deflection, the galvanometer is 0. So I have to measure a length from A to C, that is taken as L1. That means this V suffix AC is directly proportional to L1, correct? Don't you think that V suffix AC will be nothing but EMF of the cell, that is E1. That is E1 in this. Generally it is equal to EMF, but what is EMF? E1. Means, can I conclude that according to the principle, V suffix AC is directly proportional to L1, but we proved that V suffix AC is equal to what? E1, which means E1 is directly proportional to L1. I think you followed. No confusion, right? Repeat the same thing, whatever I explained, with the cell of EMF E1, with the cell of EMF E2. See, you know already, for your convenience, I removed that part, right? There was one more cell of EMF K2, one more cell of EMF E2 connected to a key K2, connected to the same terminal of the galvanometer, right? Now what you are supposed to do is, K2 will be closed Continue. K1 should be open. Then you have to repeat the same thing. For your reference, I will redraw that circuit diagram. Okay. This is a potentiometer. This is a terminal A and terminal B. Between the terminal A and B, there is an alloy of length 1 meter in our discussion. And in the primary circuit, you are having one battery. And the negative of the battery is supposed to be connected to the rheostat. Rheostat you can include, but I said I won't include. I already include once in the beginning in the original circuit. I am performing only one trial, so I am not going to change the current, so I won't include rheostat. Clear? Fine. Then from A, there is a connection given to the positive terminal of the cell of EMF E1, and negative is connected to the galvanometer, one of the terminal, right? And again from A, there is a connection given to the positive terminal of the second cell of EMF E2, and connection is given to the negative terminal is connected to the galvanometer, and galvanometer to the sliding contact. Of course, Q was included, right? Here K1, here K2. Now what I will do is, since I have to close K2, key K2 is closed, then K1 is kept open, key K2 is closed and K1 is kept open. It should be like this. K2 is closed, K1 is open. Is as good as saying that I can remove this part of the circuit, no? Open circuit. So I'll go for that. So this is let it be. K1 was closed, K2 was open earlier. That's why I removed this, correct? This explanation matches with this. Now, since K1 is open, I need not include that part of the circuit at all. Just to avoid a confusion, I'll remove that part and I'll just draw the remaining circuit where there is a cell of EMF E2 connected to the one terminal of K2, correct? And the key is closed and other end of K2 is connected to a galvanometer, and that is connected to a sliding contact or your pointer. I said do the same thing. What do you mean by repeat the same thing? Keep the jockey in contact with the wire, or sliding contact in contact with the wire fixed between A and B, near end A. Pointer and the galvanometer show deflection to one side. Keep on shifting sliding contact in contact with the wire to various positions. Let us say at one particular position, somewhere here at D, deflection read by the galvanometer was 0. Deflection read by the galvanometer is 0 means, don't you think that the current flowing through the galvanometer is 0? Fine. Now think. Current through the galvanometer is 0. What is the current in this part? 0 only, no? Because it is the same branch. What is the current here? 0. What is the current here? 0 only, because it is a single branch. Now coming to the point. Wherever you got a deflection in the galvanometer 0, measure the length, I can take it as L2. Current here indicating 0 means you refer the point D and negative terminal of the battery. This cell. D and negative terminal of the cell of EMF E2. Is there any conducting path? Yes. Is there any current now? No. Indicating that D and negative terminal of the cell are at same potential, correct? Similarly, is there any conducting path between A and positive terminal of the cell? Yes. Is there any conducting? There is a conducting path. Is there any potential difference? No. That is why there is no current here. Which means, can I conclude like this? A and positive terminal of the cell are at same potential. D and negative terminal of the cell are at same potential. Which means potential difference across AD, there is some potential difference across AD, will be equal to potential difference across the terminals of the cell. Potential difference across AD will be equal to potential difference across the terminals of the cell, or terminal potential difference. Can I say that this terminal potential difference again will be equal to EMF of the cell? Yes, because cell is in the open circuit. What do you mean by cell is in the open circuit? When we say that the cell is in the open circuit, when no current was drawn from the cell. Cell is connected here. Do you have any current in this part? Do you have any current in this part? Or when the cell is connected to any other part? No, right? There was no current drawn from the cell, indicating that cell is in the open circuit. That time terminal potential difference will be always equal to EMF of the cell, which means this V suffix AD, that is the potential difference across A and D, can be equal to what? EMF of the cell. So here also answer is the same. Cell is in open circuit. When cell is in open circuit, what do you mean by cell is in open circuit? Since there is no current drawn, right? Whenever cell is in the open circuit, you should know that terminal potential difference is always equal to EMF of the cell. So this potential difference across AD is equal to potential difference across the terminals of a cell, that is equal to EMF of the cell. Again, going back to the principle of a potentiometer, which says that V is directly proportional to L. Potential gradient is a constant, basic principle of a potentiometer. Instead of saying V suffix AD is directly proportional to the corresponding length, can I say that E2 is directly proportional to L2? Correct? So for equation 1 and 2, you know that in both the trials current was the same. When current was same, referring the previous discussion, V is equal to I rho L by A. This portion is a constant. V is directly proportional to L. Now that V will be equal to EMF here. Correct? Can I say constant here and constant in this case is same? Because in both the trial I am using the same battery where I am using the same current in the circuit. So constant in both the cases are same. We can take it as phi. E1 is equal to phi into L1. E2 is equal to phi into L2. My aim is to compare the EMF, right? So if I compare the EMF, E1 by E2 is equal to, can I say constant will get cancelled? What you are left out with? L1 by L2. See, problem is solved. Our aim is to find out E1 and our aim is to find out E1 by E2. No. We were not knowing E1, we were not knowing E2, but experimentally can't you find out L1, can't you find out L2? Of course you can call it as a balancing length, because why it is called as balancing length? Because at that length only the deflection in the galvanometer has become 0. Can't you find out L1 and L2? Substitute L1 and L2. The ratio of L1 by L2 itself is a ratio of the EMF. This is the first experiment, comparing the EMF of the two cells. So highlighting point is this one. Why I am telling you that? Terminal potential difference is equal to EMF of the cell. Terminal potential difference is equal to EMF. You can say terminal potential difference will be equal to EMF only when the cell is in the open circuit, means no current should be drawn from the cell by the other circuit element. Under that condition only you can say this V can be replaced as E1, that V can be replaced as E2. I think ideas are clear to you. Okay, so we'll take up the next one to determine the internal resistance of a cell. I am talking about the second application, determining the internal resistance of a cell. Using a potentiometer. I'll refer a same potentiometer where there is a wooden frame. On this wooden frame there is an alloy wire of uniform thickness is fixed between the 2 points. We'll name the points as A and B as before, and primary circuit is same. From A there is a connection given to the positive terminal of the battery, and from the negative terminal of the battery connection can be given to the rheostat. You can avoid rheostat also, depends upon the requirement. Okay. This circuit symbol of a rheostat. This circuit is same as a previous discussion. That is why it is called primary circuit. Now you will be given a cell. You will be given a cell, not two cells, one cell. Of course, this here I am using the battery. You will be given a cell whose internal resistance you are supposed to find out. See what are the other connection. From A, take a wire, copper wire. Other end of the copper wire is connected to a cell. It has got some EMF. Negative of the cell is directly connected to the galvanometer. And other end of the galvanometer is connected to a sliding contact. Don't you think this circuit diagram is same as the previous one? Compare it. Only key is removed, that's all. Key is not required. Because in here I am using one cell. There is no question of one side use one cell, next side use another cell, no. So earlier what we have done is, once we are using one cell, that time K1 was closed, K2 was open. Next you are using a second cell, K2 was closed, K1 was open, correct? In addition to this, some additional connections are also there. Take a wire from the positive terminal of the cell, connect it to a resistance box. You know the resistance box. In one of the session earlier, sir has already showed you the resistance box, where you can keep some standard resistances, wire wound resistor. So whatever the resistance I keep in the resistance box, I am going to represent as R. Resistance box has got two terminals, and from the other terminal take a wire and connect it to a key. The purpose of using a key is, here also we perform two trials. Once we will open the key and perform the experiment, later we close the key and perform the experiment. And other end of the key should be connected to the negative of the cell. Yeah. Let us begin the experiment. Key is open first. Remember, the aim of the experiment is to determine the internal resistance of a cell. For your kind information, the cell along with the EMF, it has got some internal resistance. The question is, what is internal resistance? When the key is kept open, think practically. Don't you think there is no use of this part of the circuit? You keep any resistance in the resistance box, maybe 1 ohm, maybe 10 ohm, maybe 100 ohm, maybe 1000 ohm, doesn't make any difference, because key is open means resistance box is in the open circuit. Better to remove it, no? When the key is open, better to ignore this part and perform the experiment. When the key is kept open, this potentiometer, A and B are the two terminals. There is alloy wire fixed between A and B, and from A there is a connection given to the positive terminal of the battery and negative terminal of the battery to the rheostat. Rheostat is connected to B, right? Since key is open, I will draw the circuit diagram without this part, no confusion. If I remove that part, there is a positive terminal of the cell of EMF E, internal resistance R, connected to the galvanometer, other end is connected to the jockey or a sliding contact. Repeat, do the experiment. Keep the sliding contact in contact with the wire near NDA. Pointer in the galvanometer will be in one, it will show deflection to one side. However, here also conditions will apply. That is the thing first you have to check. EMF of the battery should be greater than the EMF of the cell. How to check? I told you. When you keep a sliding contact in contact the wire near NDA, pointer in the galvanometer should show deflection to one side. When you keep in contact the wire near NB, the pointer should show deflection to the other opposite side, indicating that EMF of the battery in the primary circuit is greater than the EMF of the cell in the secondary circuit. That is verified. Then you repeat the experiment what you performed earlier. You keep on moving the sliding contact in contact with the wire at various positions till the deflection read by the galvanometer is 0. Assume that when the sliding contact was in contact with the wire at position C, the deflection was 0. Then you measure the length. You can call it as a balancing length L1. L1 is a balancing length when the key was open. I have removed that part. Now the galvanometer is showing a 0 deflection, means current through the galvanometer is 0, correct? Current through the galvanometer is 0 means what is the current here? 0. What is the current here? 0, correct? Single branch, current throughout should be same. Here it is 0 means everywhere it is 0 only. Which means, look at C and a negative terminal of the cell. Is there any conducting path between the negative terminal cell and C? Yes, there is a conducting path. Do you have a current? No. Indicating that this C and negative terminal of the battery are at, negative terminal of the cell are at same potential. Similarly, A and positive terminal of the cell are at same potential, which gives a clear indication that potential difference across AC is equal to potential difference across the terminals of the cell. Can I say this is equal to EMF of the cell only? Yes, you have to agree. Already I explained in the previous. Why this potential difference across the terminal cell is equal to EMF? Because cell is in the open circuit. When we say that the cell is in the open circuit, when no current was drawn from the cell by the other circuit element. So do you have any current in this part? Do you have any current in this part? No. And even if there is a resistance box also here, it is not drawing any current because key is open. If you are having that idea, you removed that resistance box. Yeah, I removed resistance box, but key was open. No. Open circuit, it is not drawing any current, which means cell is in the open circuit. Since cell is, what do you mean by cell in the open circuit? Because no current was drawn from the cell. That's why terminal potential difference is always equal to EMF, which means potential difference across AC, that will be equal to what? EMF of the cell. And when it is equal to EMF, can I write, instead of writing V is directly proportional to L1, can I write E is directly proportional to L1? Same as before. Basic principle is V by L is a constant. V is directly proportional to L. Since V is equal to E, E is directly proportional to L1. I hope you understood this. Okay, now we'll repeat the experiment with key closed. Should be careful, listen. With keys closed. I'll draw the circuit diagram. Same potentiometer. There is a Li wire fixed between A and B, and from A there is a connection given to the positive terminal of the battery in the primary circuit. Negative terminal can be connected to the rheostat, other end of the rheostat is connected to the B. Next, from A, I had to give a connection to the positive terminal of the same cell whose EMF is E and internal resistance is small r, connected to a galvanometer, and it is connected to a sliding contact. Then from the positive terminal of the cell there is a connection given to the resistance box where you are going to keep some resistance, and it is connected to a key, and the other end of key is connected to the negative terminal of the cell. Same circuit, but this time key should be closed. Key is closed. I kept some resistance in the resistance box for your information. Remember, this key will not have a resistance, just like a metal strips, they don't have a resistance. Key, copper wires, their resistance is negligible if they have also. Repeat the same thing what we are doing throughout till now. Take the sliding contact, keep the sliding contact in contact with the wire near NDA, pointer in the galvanometer will show deflection to one side. Keep on moving the sliding contact in contact with the wire. Keep on moving the sliding contact in contact with the wire. Let us say when the sliding contact was kept in contact with the wire at some point D, deflection read by the galvanometer is 0. When the sliding contact was kept in contact with the wire near point D, deflection read by the galvanometer is 0. Deflection read by the galvanometer is 0 means current flowing through a galvanometer is 0. No. Can I take up this length as L2? That you have to record. L1 you have to record, L2 you have to record. Difference is L1 is a, you can call it as a balancing length. Why we call it as a balancing length? That time the current flowing through a galvanometer is 0. L1 is a balancing length when the key is open. L2 is a balancing length when the key is closed. What is the current flowing through the galvanometer? 0. What is the current in this part? 0. What is the current in this part? 0. What is the current in this part? 0. Correct? Which means D and negative terminal of the cell are at same potential. Continue. A and positive terminal of the cell are at same potential, which means I can conclude that potential difference across AD, correct, is equal to potential difference across the terminals of the cell. Same statements are repeated almost 4 times. Potential difference across AD is equal to potential difference across the terminals of cell, that is for sure. Means if you connect a voltmeter across A and D and voltmeter across positive and negative terminal of the cell, both the voltmeter will read a same reading. That is a practical meaning. Potential difference across AD is equal to potential difference across the terminals of a cell. Now coming to the climax, is it equal to EMF of the cell? This time no. It is not equal to EMF because cell is not in the open circuit, cell is in the closed circuit. You know why? Cell is said to be in the closed circuit when current was drawn from the cell by the circuit element. Don't you think that since this key is closed, since that key is closed, this part of the circuit consisting of a resistor and a wire connected across the cell will draw some current from the cell? Yes. That is why this potential difference across the terminal cell will never be equal to EMF. It is less than EMF, for your kind information. Because now this is the only one case where in all our discussion this cell is said to be in the closed circuit. Till now everywhere cell was in the open circuit, but here cell is in the closed circuit. Why I said cell is in the closed circuit? Even though the potential difference across AD is equal to potential difference across the terminals of the cell, but that is not equal to EMF because cell is not in the open circuit, cell is in the closed circuit. Why I am telling you that cell is in the closed circuit? Because the current was drawn from the cell by this part of the circuit element. Resistance box, key is closed. Means this is not equal to EMF. It will be equal to V only. It will be equal to V only. Think slightly more. If you connect a voltmeter across A and D, connect voltmeter across positive and negative terminal of the cell, take one more voltmeter and connect across the resistance box. Don't you think all the three voltmeter will read the same reading? They are connected in parallel, for your kind information. You may be thinking, galvanometer is there. No, we already proved there current through the galvanometer is 0. Then why we have to bother? This D and this negative terminal are at same potential. There is no current flowing through the galvanometer, even though galvanometer is there having a resistance, correct? So potential difference across AD is equal to potential difference across the terminals of a cell is equal to, can I say, potential difference across this resistance R, which is kept in the resistance box. Got it? It is not equal to EMF of the cell. That is the point to be noted. Here cell is in the closed circuit. Cell is in the closed circuit. That is why it is not equal to EMF. It is equal to V only. V will not be equal to EMF. V will be less than EMF. I hope you understood this. That means here I can't write E is directly proportional to L2. Here I should write V is directly proportional to L2. This is the difference. I'll repeat. Even though potential at D is equal to potential at negative of the battery, potential at A is equal to potential at the positive of the battery, which means potential difference across AD is equal to potential difference across the terminals of cell, but this time it is not equal to EMF because cell is in the closed circuit. It is equal to EMF only when cell is in the open circuit, but here cell is in the closed circuit. What made me to say that cell in the closed circuit? Because there was a current drawn from this part of the circuit element by the cell. Even though there is no current here, but there is a current drawn from the cell by this part of the circuit element. That's why cell is in the closed circuit. That's why EV will not be equal to E here. V is directly proportional to L2. Look at equation 1 and equation 2. We will wind up the discussion by substituting. I will write few steps here. Of course, this is a circuit diagram already there. So I am comparing equation 1 and 2. Don't you think that the constant here and constant here are the same? Obviously, in both the cases, the current I am using from the battery primary circuit is same. So I can divide equation 1 by 2. If I divide equation 1 by 2, E by V is equal to L1 by L2. L1 is the balancing length measured when the key is open. L2 is the balancing length measured when the key is closed. This V and E and V have to simplify. How to simplify? Don't you think this V can be rewritten as ER by R plus R? V here, V here, V here are same, no? V here and V here are same. So this V is a terminal potential difference Formula for a terminal potential difference you already learnt in the cell. This formula I have recalled in the beginning of this session. This V can be replaced as ER by capital R plus small r is equal to L1 by L2. Can I cancel this E? So if I continue here, you will get capital R plus small r by capital R will be equal to L1 by L2, right? Or this can be written as 1 plus small r by capital R is equal to L1 by L2, correct? Or small r by capital R is equal to 1, I will shift to the other side, L1 by L2 minus 1, correct? Or if I take a common denominator and do the cross multiplication, L1 minus L2 by L2 multiplied by R means capital R into L1 minus L2 divided by L2. This is a formula to be remembered. In your experiment, you will use this formula in calculating internal resistance of a cell. What is capital R? You will be knowing what you are going to keep in the resistance box. L1 and L2 you find out. L1 is a balancing length when the key is open, L2 is a balancing length when the key is closed. Substitute the values, you are going to get the internal resistance of a cell. I hope you understood this discussion. And I told you in the beginning only, this year in physics practicals, you will be performing both the experiments, comparing the EMF of the two cells as well as determining the internal resistance of a cell, two separate experiments. So altogether what you can highlight here is 4 experiments will be covered in your practical section from meter bridge onwards till potentiometer. I think the logic is clear to you. I hope you followed. See, this is all about this entire topic, current electricity. So this is the last part, that's over. Few numericals I will solve in the next discussion. Is it clear?